Hello everyone, I am Santosh KG, Assistant Professor, Department of Mechanical Engineering, MIT, Mysore. In today's session, I am going to teach you the topics rotating unbalance and reciprocating unbalance, which comes under the forced vibration, which is the module 5 of subject dynamics of machines having subject code 18ME53. Now let us start the topic rotating unbalance. So where we experience the rotating unbalance, we are going to experience the rotating unbalance in the rotating machines. So what is a rotating machine? So a machine which is consisting of a rotor as a part, then such machines they are called as a rotating machines. All the manufactured rotors they are having some amount of eccentricities. It may be because of the defects in casting, or it may be due to the presence of the keyways, or it may be due to the non-uniformity of welding. Now, in order to understand the rotating unbalance, let us consider a rotating machine which is having mass capital M, and the rotating unbalance is represented by the rotating mass of magnitude small m as having eccentricity E, and let us say it is rotating with an angular velocity omega. At a given instant of time, let us say this mass is making an angle of omega t with respect to the horizontal axis. This machine is mounted on a foundation having the stiffness K and the damping coefficient C. Let us say at the given instant when this mass m is rotating with an angular velocity omega, it produces a centrifugal force which is equals to m omega square E. So due to this centrifugal force, there will be certain amount of unbalance generated in the machine and it starts to vibrate, and at a given instant of time, let us say the non-rotating parts gets displaced by an amount equal to small x from the static equilibrium position. So when the non-rotating parts, if they displace by an amount equal to x, then the rotating parts they are going to display by an amount equal to x plus E time sin omega t. So x it represents the displacement of non-rotating parts, and x plus E sin omega t it represents displacement of rotating parts. So here, since m represents the total mass of the machine and small m it represents the mass of the reciprocating mass, therefore the non-reciprocating masses will have the magnitude capital M minus small m. So capital M minus small m it represents the mass of the non-reciprocating parts, and small m it represents the mass of the reciprocating parts. Now let us try to apply the Newton's second law. for the rotating machine. So the Newton's second law is given by equation m into A equals sigma times F. So m represents the mass of the total machine and A represents the acceleration. So this will be equals to the sum of the external forces that will be acting on the given rotating system. While representing the inertia forces for the rotating machine, it will be having two parts. One is the inertia force due to the non-reciprocating masses, and the second is the inertia force due to the rotating parts having mass small m. So the non-reciprocating parts, it is having the mass capital M minus small m and their displacement is x. So if the displacement is x, then the velocity will be x dot and their acceleration is denoted by x double dot, plus the rotating masses is having magnitude small m and it is displaced by an amount equal to x plus e times sin omega t. So if I differentiate this term once with respect to t, I will get the velocity, and if I differentiate the same term twice, then I will get the acceleration. Therefore, the acceleration of the rotating parts, it is d by dt square of x plus e into sin omega t. So this will be equal to the sum of the external forces that will be acting on the given rotating machine. So the external force that will be mainly generated on this rotating machine will be due to the spring of stiffness K and the damper of damping coefficient C. So due to the spring of stiffness K, we get the force which is of magnitude Kx, and due to the damper C, we get the damping force of magnitude Cx dot, and these two forces, it will be opposite to that of the displacement. Here, if the displacement is taking place in the vertically upward direction, then this spring and damper, they will try to bring this system to the equilibrium position by applying the force in downward direction. So since these two forces, they are acting opposite direction to that of the displacement, these two forces, they should be represented with the negative sign. Now I will simplify this. So before simplifying this equation, first I am going to differentiate this term. So this term is d by dt square of x plus e into sin omega t. So in order to differentiate it twice, first I will differentiate this term with respect to t once. So when I differentiate this term with respect to t once, then I will get, so the differentiation of x with respect to time t is dx by dt, which is denoted by x dot, plus e is a constant and the differentiation of sin omega t is cos omega t, and the differentiation of omega t is omega. Therefore, the d by dt of x plus e sin omega t will be equals to x dot plus omega into e into cos of omega t. Now in order to get d by dt square of this term, I need to differentiate this term with respect to t. So when you differentiate x dot with respect to t, I will get x double dot plus, here omega into e, it represents a constant, therefore I am going to write it as it is, and the differentiation of cos omega t is minus sin omega t into omega. By simplifying this, I will get x double dot plus into minus minus omega into omega, omega square into e into sin omega t. So this is the d by dt square of x plus e sin omega t. Now I am going to substitute this value in this equation and I am going to simplify this. So the first term we are having is m minus m into x double dot plus small m into, in place of d by dt square of x plus e sin omega t, I am going to write x double dot minus omega square into e into sin omega t. So this equals minus kx minus c into x dot, m minus m into x double dot plus, I am going to send this m inside the bracket, thereby I get m x double dot minus m omega square into e sin omega t equals minus k into x minus c into x dot. Now I am going to take these two terms towards the left hand side and I am going to send this negative term towards right hand side. Thereby I get capital M minus small m into x double dot plus m x dot m x double dot. When I take these two terms towards left hand side, these two terms will be positive, thereby I get c into x dot plus k into x equals m omega square e into sin of omega t. Now I will take this x double dot inside the bracket, thereby I get mx double dot minus m into x double dot plus m into x double dot plus cx dot plus kx equals m omega square e into sin of omega t. Here this mx double dot and this mx double dot, they will cancel out because they are having same magnitude with opposite sign, and the remaining terms we are having is capital M x double dot plus cx dot plus kx equals m omega square e into sin of omega t. So this is the expression we got by applying the Newton's second law for a rotating machine. I will call this equation as 1. Now I will compare this equation with the simple harmonic motion for a spring mass damper system which is undergoing forced vibration, and the equation is given by mx double dot plus cx dot plus k into x equals f naught into sine omega t, and I am going to call this as equation 2. Now, if we compare equation 1 with respect to equation 2, we get the value of f naught as m omega square into E. Once we derive the differential equation of motion for the rotating unbalance, now let us try to find the steady state amplitude and the phase difference phi for this rotating unbalance. So, the steady state amplitude for the forced vibration in general is given by x equals f naught divided by square root of k minus m omega square whole square plus c into omega square. For the rotating unbalance, the value of f naught is m e omega square and the value of m is capital M. Thereby rewriting the equation, I get x equals, in place of f naught, m e omega square divided by square root of k minus capital M omega square whole square plus c omega square. Now, let us try to express this steady state amplitude equation in non-dimensional form. In order to express this equation in non-dimensional form, first I am going to divide the numerator and denominator of this equation by k. Thereby, I get capital X equals m e omega square divided by k divided by square root of capital K minus m omega square plus c into omega whole square divided by k. Again, m e omega square divided by k whole thing divided by square root of, if I take this k inside the brackets, I will get 1 minus m omega square divided by k whole square plus c into omega divided by k whole square. After writing this, now in order to get the non-dimensional form, again for the numerator I am going to multiply and divide by capital M. We know that capital M divided by k can be written as 1 divided by omega n square, and c omega divided by k, it can be written as 2 times zeta omega divided by omega n. Therefore, the value of x equals, so in place of m by k, I can write 1 divided by omega n square, and in the numerator I am having omega square. Therefore, omega square divided by omega n square, I can write it as omega divided by omega n square. The remaining terms are, in the numerator I am having small m multiplied by E, and in the denominator I am having capital M divided by square root of, inside the bracket I am having 1 minus, in place of m by k I can write omega n square, but in the numerator I am already having omega square, thereby I can write omega divided by omega n square whole square, plus in place of c omega by k I can write 2 times zeta omega divided by omega n square. Now still this equation is not in the non-dimensional form. So in order to get it in non-dimensional form, I am going to send m into E divided by capital M towards the left hand side, thereby I get capital Mx divided by small m into E in the left hand side, and this equals omega divided by omega n square divided by square root of 1 minus omega divided by omega n square whole square, plus 2 times zeta omega divided by omega n square, and this represents the non-dimensional form for the steady state amplitude when the given machine is having the rotating unbalance. Till now we derived the expression for differential equation of motion and the steady state amplitude for the rotating unbalance. The differential equation of motion for the rotating unbalance, it is given by capital M into x double dot plus cx dot plus k into x equals m e omega square into sin omega t, and the steady state amplitude is given by capital X equals small m e omega square divided by square root of k minus capital M omega square whole square plus c omega square, and in the non-dimensional form it can be expressed as capital Mx divided by small m into E equals omega divided by omega n square divided by square root of 1 minus omega by omega n square whole square plus 2 zeta omega divided by omega n square. Now let us try to find what will be the phase difference phi for the rotating unbalance. So in general, for the forced vibration, the phase difference phi, it is given by tan inverse of c omega divided by k minus small m into omega square. But for the rotating unbalance, the same equation we can rewrite as phi equals tan inverse in bracket c omega divided by k minus, in place of small m I should replace capital M into omega square. Now let us try to express this phase difference phi in the non-dimensional form. So in order to express in non-dimensional form, I need to divide the numerator and denominator of this equation by k. So by dividing the numerator and denominator by k, we get phi equals tan inverse of, in numerator I get c omega by k, and in denominator I will get k minus m omega square divided by k. Again, simplifying this equation, we get phi equals tan inverse of c omega divided by k, and in the denominator I will get 1 minus m omega square divided by k. We already derived that c omega divided by k, it can be replaced by 2 zeta omega divided by omega n, and capital M divided by K, it can be written as 1 divided by omega n square. In the nominator of this equation, I am having C omega divided by K. I am going to replace it by 2 zeta omega divided by omega n, and in the denominator I am having 1 minus, here I am having the ratio capital M divided by K. So, in place of capital M divided by K, I can write 1 divided by omega n square. So, in the numerator we are having omega square, in the denominator we will be having omega n square, thereby I can write it as omega divided by omega n square, and this represents the non-dimensional form of phase difference phi for the rotating unbalance. After analyzing the system which is having rotatory unbalance, now let us try to analyze a system which is having the reciprocating unbalance. So, here we have considered a machine which is having the reciprocating unbalance due to this slider which is having the linear reciprocating motion. Let capital M, it represents the mass of the entire reciprocating machine, and small m, it denotes the mass of the reciprocating parts. Thereby capital M minus small m, it represents the mass of the non-reciprocating parts. When the crank which is having an radius E, it is rotating, it produces the reciprocating unbalanced force, because of which the machine gets displaced by an amount equal to small x. So, x, it represents the displacement of the non-reciprocating parts of this machine. If x is denoting the displacement of non-reciprocating parts, then the displacement of the reciprocating parts, it will be given by x plus E into sin omega t plus E by L into sin of 2 omega t, and this machine is mounted on a foundation which is having stiffness K and the damping coefficient C. Now, let us try to apply the Newton's second law for this machine and derive the expression, differential equation of motion for this system. So, we know that the Newton's second law, it is given by m into A equals sigma into F. Since this machine is having both the reciprocating as well as the non-reciprocating parts, and also there is a different displacement of the reciprocating and non-reciprocating parts, the inertia force, we will get two terms. So, first inertia force will be because of the displacement of the non-reciprocating parts, and the second inertia force is due to the displacement of the reciprocating parts. So, the non-reciprocating parts, it is having a mass of capital M minus small m, and its displacement is given by x dot. Therefore, the acceleration due to the non-reciprocating parts will be capital M minus small m into, if you differentiate the displacement twice, we get the acceleration which is denoted by x double dot, plus the inertia force due to the reciprocating mass will be given by mass of the reciprocating parts times double differentiation of the displacement of the reciprocating parts, which is x plus E sin omega t plus E divided by L into sin of omega t. Here E, it represents the radius of the crank and L represents the length of the connecting rod. This equals summation of the external forces. So the external forces we get here because of the spring having stiffness K and damper having damping coefficient C. So the spring force is given by Kx and the damping force it is given by Cx dot. And these two forces, since they are acting opposite to that of the displacement, they are denoted with a negative sign. Now I will simplify this equation. Here compared to E, the length of L is very much larger. So if we divide E by L, we will get a quantity which is less than 1, and if you double differentiate it, so the effect of this term will be negligible. So I am going to neglect this term. So when I neglect this term, then if I simplify this equation, so first we are having capital M minus small m into x dot plus m into the differentiation of x plus e into sin omega t is x dot plus e omega cos omega t. And if you again differentiate that, we will get x double dot minus e omega square into sin of omega t. Therefore, m into x double dot minus e omega square into sin of omega t equals, in the right hand side we are having minus cx dot minus kx. Again I will take this x double dot inside the bracket, thereby I get capital M into x double dot minus small m into x double dot plus I am going to send m inside the bracket, thereby I get m into x double dot minus m e omega square into sin omega t equals minus cx dot minus kx. So here minus mx double dot plus mx double dot will cancel out, and I am going to send these two negative terms towards the left hand side and this negative term towards the right hand side, thereby I get the equation mx double dot plus cx dot plus kx equals small m e into omega square sin omega t, and this represents the differential equation of motion for a system which is having reciprocating unbalance. So if you observe this equation, it is same as the differential equation of motion for a system having the rotary unbalance, thereby we get the expression, we get the same expression for the steady state amplitude as well as phase difference phi for both the reciprocating unbalance and the rotary unbalance. So the steady state amplitude x for the reciprocating unbalance, we can write it as m into e into omega square divided by square root of k minus capital M into omega square plus c omega square. And in the non-dimensional form, we can write the same equation as capital Mx divided by small me equals omega divided by omega n square divided by square root of 1 minus omega by omega n square whole square plus 2 zeta omega divided by omega n square. And coming to the phase difference phi it is given by tan inverse of c omega divided by k minus capital M omega square, and in the non-dimensional form it can be written as phi equals tan inverse of 2 zeta omega divided by omega n divided by 1 minus omega by omega n square.